Okay. So last time we formulated the following theorem. That geodesics in the Riemannian manifold locally minimize the length of curves. So namely, theorem went like this. Let xg be a Riemannian manifold and let me fix point in x and consider some neighborhood of 0 in Tpx. So this is open ball which is also a normal neighborhood of 0. I can write contained in a normal neighborhood, and also I would like to denote NP to be image of exponential of n0 and for any q in NP, let gamma be a smooth curve from 0, 1 to NP, be a unique geodesic such that, well, it connects P and Q, so gamma of 0 is P, gamma of 1 is Q. Yes, that's it. Then statement is that for any other curve in X, well, so it's curve gamma from 0, 1 to X such that it connects P and Q. Yes, and this one I would like to denote as gamma PQ. And gamma is any other curve such that gamma of 0 is P, gamma of 1 is Q. And it can go outside of NP. We have that length of gamma is strictly greater than length of gamma of PQ. So that's the thing, and idea was to prove this in like geologically spherical coordinates. So I had sphere, so this is unit sphere. And I have also this map rho from the product of some interval. So this is unit sphere in where? In Tpx. And I have also this map from this product to well, to Tpx. This is just spherical coordinates really. So I take T and then element here, V and consider TV in TPX. So actually, I would like it to go to N0 and without 0, and I would like it to be diffeomorphism. So since N0 is an open ball, this is basically the radius of this ball. And then I define phi to be composition of exponential and rho. Yes, and so we define the following formula that pullback of G with respect to phi is actually, well, it is a form in here, well, two form. So should not say two form because two form lives in, it's anti-symmetric, right? But this is symmetric, so it's this guy is in S2 of T star of this, and this is written as dt squared plus plus sum omega I bar, where omega I bar was defined as follows. So here it's I from 1 to n is dimension of x. And so my g actually was, so what is omega I bar here? My g was actually the sum, maybe I have to write omega I square here. Yeah, omega I square. G is actually omega sum over I from 1 to n omega I square without bar. Actually, right. So where omega I is just defined at my point P. So I have omega. So my omega. So well, I have to remind this. So I have psi1, psi n. So this is basis in TPX, right? Such that at point P I have this is orthonormal basis with respect to G, so delta ij here. And we also had this that omega I at point P at psi j is delta ij. And to every other point, you actually, well, this is in, I should say, on where? Well, on NP. So it's not globally, but omegas are forms on NP. So this NP is the image of a normal neighborhood. And where you define at P the values of omegas like this, and then you use parallel translation with respect to unique geodesic, to get a point of omega at any other point in NP. Right. So this was our stub.
What are omega I bar?
Yes, omega I bar was the following thing. So we actually proved that phi star omega I. So it's one form again in this. It's written as dt fi dt. So this is some function that actually we considered what is this function, and plus omega I bar. So basically you have coordinates in here. One coordinate is related to this interval and coordinates on S. So omega only is expressed in D of coordinates on S. So this was our omega I bar. Yes, and so we had this. All right, now let us use this. Let us use this. So let me first, well, this gamma in our theorem can go outside, but first let me consider gamma inside. All right, so let gamma be like in theorem, in formulation of theorem. So it means that, well, I fix my 2 points, P and Q, and gamma of 0 is P, gamma of 1 is Q, and also it is gamma is from 0, 1 to NP first. Then I actually can consider, well, phi inverse of gamma of t, since it's inside NP. Well, this will be, some curve inside here. Well, phi inverse up to, well, of OT except 0. This is some technical moment I can drive. Since I'm working in spherical coordinates, I don't want 0 included. So this will be then T of S, V of S. So some pair, right, actually a pair, one is just some function in here that, well, maybe I want this argument to be S, right? So this is just a pair that lives in here. So this is just curve in here, right? So for every S from 0 to 1. So I exclude 0. So let me denote this as just gamma 0 of S with this pair. Okay, then I'm going to compute. Okay, so this I'm going to erase, fortunately. So I'm going to compute the length of gamma. Well, I excluded just 1 point, doesn't really matter, right? So I can actually do it in spherical coordinates. So it's integral from 0 to 1, and then right, phi star of G of gamma 0 of S. Well, this is just of T of S, and then, well, so this is tangent vectors, so I shall put gamma 0 prime of S, and then gamma 0 prime of S ds. So it's just a change of variables. Okay. Then I use this boxed formula. So this will be integral from 0 to 1 of. So I have t prime of s. Again, I forgot 1/2 here, right? So squared plus sum over I omega I bar v prime of s squared, and then take square root of this ds. So L of gamma is written as follows, right? So maybe I forgot to close parentheses here, and I'm going to use this formula now. So the goal is to see is that if gamma equals gamma pq, then actually this term is gone, right? And if it's not, then we have this term, which is greater than 0. And this will give us the result. Okay, so let me introduce V, which is the preimage of Q with respect to exponential map. So let Q be exponential of some V. Well, just from the definition of exponential map, Q is gamma V of 1, right? Where this is geodesics going from P with tangent vector V, right? So this is geodesics. So actually then we know that what I denoted by gamma PQ there, unique geodesics, is actually just gamma V. Well, I also should check that actually it's from 0 to 1 and value to 1 is Q, but this is exactly what happens here. Because I can consider different parameterizations, of course, but all right, now what else? Let me take gamma PQ. So I'm computing T gamma 0 of S when my gamma is gamma PQ. That's what I'm doing right now. So let me take gamma PQ and consider X inverse. So first I have to apply XP inverse of S. So this is the same as X inverse of gamma of V of S. So this is the same as X inverse of gamma SV of 1. And this is SV. So my geodesic in N0 just looks like this. It's just this vector V gives me direction, and I go by straight line in this direction. And then I have to take rho inverse of that. Right, so I computed how does it look like in N0. Then rho inverse, well, I have to normalize V. So it will have norm 1. It will live in S, and what happens with parameter will live in here. So actually I have that phi inverse of gamma PQ of S is just this S, and then So I have to divide by norm of v and multiply by norm of v. So I have s norm of v and then v divided by norm of v. So this is my gamma 0 if gamma is equals gamma pq. Okay. Okay. Where is this? So just to draw a picture, so this is my n0, and any geodesic from P in n0 just looks as path which just goes along radius of n0. So this is actually 0 and this is 1. I mean s equals 0 and well, but I rather should take like exponential inverse of p here, and this is exponential inverse of p. Okay, so therefore my v, if I have geodesics, gamma is geodesic, then my v of s, which is just this thing, it does not depend on s. So v of s is constant, and therefore v prime of s is 0. Right? And I can actually compute that L of gamma pq is just, okay, I'm using this. It's integral from 0 to 1. This is 0, right? Because this is 0. And I will just have absolute value of t prime of s. And t prime of s is just norm of v. So it will be just norm, it will be just norm of v ds. And this is just norm of v. Okay, this is the length of geodesic. On the other hand, if, let me now consider gamma, which is not gamma pq, so it's not geodesic, but it's still in NP, then this actually means, well, it differs from this one, right? Because, and so therefore it means that v prime of s is not 0. So any other path that I take, I should change and go a little bit, right? Okay. Or I can also, okay, I can go like this. I can go in straight line, right? But then, you know, go a little bit further and then go back. This is another option where v prime of s is 0. But in this case, a theorem follows immediately, right? Because like the path where I go along this and then a little bit further and then back is of course has length greater than gamma of pq, right? So I assume that I have something like this. Okay. So this means that there exists phi I star of omega I. So there exists I from 1 to n such that, let me not squeeze this. So the statement is that there exists I, some I, between 1 and n, such that phi star omega I of v prime of s is not 0. All right. Well, just because omega is a base is actually basis for one forms, and phi is diffeomorphism. So therefore, this is also basis on one forms on this product 0 delta s. So therefore, we should have this. Okay. So, and by not equal to 0, I mean, kind of identically not equal to 0. Right? Well, this function of s. Okay, so let me erase this. And of course, dt of v prime of s is, well, dt is 0. Right? My phi star omega I is dt phi fi dt plus omega I bar. So this leaves on the tangent space to the sphere. So dt of something that's on the sphere is just 0. So therefore, I know that omega I bar omega I bar of v prime of s is not 0. Okay. So therefore, I'm going back to here, and I know that then L of gamma, again, I'm using this this formula, is strictly greater than integral from 0 to 1 of t prime of s absolute value ds. Right. So this term is positive, right? At each point, at each s, there exists some I such that this is, this is non-negative, so at each s there exists some I such that this is non-zero. So this is actually positive. So strict inequality here, but then what? It is greater or equal than again t of 1 minus t of 0. Because again, this is just one-dimensional situation, right? It's just some function depending on s. Well, it can go like it has t of 0 here and t of 1 here, right? It can go past this and then return. And so that's therefore this inequality is here. Right, but t of 0 is actually 0 because that's the coordinate of p, right, under exponential map. So this is actually 0. So this is actually t of 1. So now I need to compare t of 1 with L of gamma pq. All right. Right. So I have that gamma of 1 is q because it connects p and q, and phi inverse of gamma at 1 coincides actually with phi inverse of gamma pq at 1, and this is just v, and then v divided by norm of v. No, I just apply phi inverse to q, and that's what I get. Just the same computation as in here. Okay, now therefore I know that T of 1 is norm of V, but we know that norm of V is L of gamma PQ. So therefore we get it, so that L of gamma is strictly greater than L of gamma PQ. So far, only for gammas that are inside N0. Okay, now let us finish the proof by assuming now that gamma goes outside. So finally, suppose that image of gamma does not belong to NP. Then, well, I can take some delta prime such that, so that's where I actually using the fact that my N0 is open ball. Actually, this argument, so if I formulated the theorem about this length only about curves that inside NP, then I don't need this open ball condition. But for any curves that can go outside, I need N0 to be open ball. Because I don't know, on a sphere, right? So suppose I'm on a sphere, and I can consider the following, or even maybe a circle, right? And I can consider a neighborhood which is just given by this. So maybe everything except maybe some interval which is close to this point that I fixed. Right, and geodesic which is inside NP that actually connects these 2 points might not be the shortest curve, right? Because I can also go like this. Okay, so the proof goes like this. I actually can take delta prime such that it's between V and delta. Norm of V and delta, right? Well, there exists some value of parameter. So since my curve goes outside, it should at some point, like any sphere that of any radius inside N0 that I choose, it should intersect, right? In particular, the one with radius delta prime, right? So there exists some S such that, well, the norm of exp inverse of gamma of S is equals to delta prime. Now let me actually denote this guy by Q tilde. So this is some point inside NP, another point. And I can actually see that L of gamma by what we proved already is, well, L of gamma in the sense that, so here I should take L of gamma between like this. I don't know how to denote it, right? Gamma from 0 to from this interval, not the whole one, but like a piece of this gamma to NP is greater than L of gamma PQ tilde, but this guy, again, by what all our computations is actually delta prime, and delta prime is greater than norm of V, which is L of gamma PQ. And we are done. Well, because the length of this, the length of a piece of interval is, of course, greater than the length of the whole.
Why didn't we need to say that the ball is open? Because if the ball is closed, we could just take delta prime as the same with delta.
Yes, I guess you can consider the closed one. It's just so you need this map phi to be diffeomorphism to an image, but I guess that's not a big problem. Yeah, I don't see any technical abstractions. Maybe there are, but they don't come to mind right now. Yeah. Okay. So so now we have this theorem, and actually this theorem allows us to.
Можете еще повторить, почему важно, что окрестность должна быть именно шахмат?
Ну, вот на самом деле в том, что у меня есть вообще есть этот дифеоморфизм. Ну, как бы я этим пользовался везде. Вот. Я говорил, что у меня есть дифеоморфизм, значит, отсюда вот сюда. Да.
Мы говорим, что рассматриваем последний случай, когда мы выше за границы области, и мы используем, чтобы дойти до границы, мы можем пройти строго больше, чем другие точки.
Ну да.
Ну, в общем, да, это свойство шахмат.
Ну да, правильно. Да, спасибо. Ну да, я мог, в принципе, как-то здесь сужать, и, может быть, действительно, это все равно был бы дифеоморфизм, но ну да, ну вот то, что было сказано. Хорошо. Okay, so let's now we can define actually metric on our manifold. So let M G again be a Riemannian manifold. Then we define the following number for each pair of points. D of PQ is just the infimum of all lengths of curves, right, that go from P to Q. So let me denote it like this. And lengths actually do not depend on parameterization, because this is just change of variable in integral. So L of gamma depends really on curve, And so this is the definition. And the statement is that actually so proposition is that actually D defines metric on M. Namely, so D is a metric on M, namely we have the following properties. First of all, first two are actually obvious, but being a metric, it's just is included in the definition of metric. So 2 is a triangle inequality. So dp q is less or equal than dpr plus drq. And the third one actually follows from the theorem that we just proved, is that dpq is 0 if and only if p equals to q. So 1 and 2 are obvious, and this, I don't know, this is proof. And 3 follows from the theorem. So Riemannian manifold is naturally admits metric. So at this point, I am kind of leaving the realm of Riemannian manifolds. Well, there are other interesting questions. For example, so what we proved was only local, and so one might ask questions like, can we, in some additional under some additional assumptions, get these statements like global versions of the statement? And the answer is actually yes, if you your additional assumption is that your Riemannian manifold is complete Riemannian manifold. So all geodesics are actually defined on whole R, which is the same as all Cauchy sequences converge. In particular, for compact, if M is compact, then any 2 points you can join by geodesic of minimal length. But okay, we don't have too much time. Let me rather go. So my next goal is to discuss curvature, and for that it's more convenient for me to actually to introduce curvature not on vector bundles, but on something much more general, which is fiber bundle. So, and what is connection on fiber, and what is fiber bundle? So let us discuss that. Нет, это не очевидно. Ну вот, кому интересно, вот хорошо в книжке Хилгасона написано. Ну вот я думал по ней дальше. Но я так оценил, сколько у нас времени осталось до конца семестра, решил, что срежем этот угол. Вот. Значит. Окей. So definition But it's not so hard to prove. So kind of the proof goes like you can like any local geodesic you can like continue a little bit like every time. So if you have like a geodesic defined on A, B, right? The clue point is that you can define it and at A, B plus epsilon, and kind of everything follows from that. But again, this is some arguments I needed to see that. Okay, so let me now define what is a fiber bundle. So let me consider, so let E, X, and F be smooth manifolds. And let pi from E to X be a smooth surjective map. Then a pair of E and this map is called, well, sometimes, well, the terminology is the same as for vector bundles, right? Sometimes this we call it fiber bundle, sometimes the projection, sometimes both, but the data is that you have both. Is called fiber bundle with fiber F if well for any point P in X there exists open neighborhood of X containing P such that and also diffeomorphism, let's call it psi P. So this diffeomorphism from pi inverse of U to U times F such that, well, it's compatible with projection. The following diagram is commutative. Let me, is commutative. And the diagram is like that. So you have pi inverse, and then you have pi psi p, you go here, and then you go to u by pi here, and to u by, how to denote p1, which is projection to the first component, just usual projection. And this is it. So basically, this is a generalization of vector bundles in the sense that a vector bundles is a fiber bundle where fiber is vector space, and you have more structure on vector bundle, which is linear structure on each fiber. Okay. So this being said, we can actually consider define what is connection in such more general situation. Definition. So again, let pi e to x be a fiber and I don't specify what is fiber here. So the vertical, well, first I need to define what is so-called the vertical bundle. So the vertical bundle, this is actually vector bundle over E. Is a vector subbundle of TE, just tangent bundle E, defined by the following. I just defined the fiber of this vector sum bundle. So VE at any point P, it is kernel of d pi, well, at point P. So P is a point, so for any P in E. Let me maybe draw a picture to simplify understanding of what's written. So basically I'm saying that, okay, I have X, right? I have, right, E at the top of X, and then I fix a point, P, right, in E, so this is my E. And at this point, well, I have a bunch of, okay, so how do I draw a tangent space to, like in this three-dimensional situation, but I have a bunch of vectors coming out of it, right? And so I only take vectors, so and I have projection, right? So this is my fiber, so it's projected to some point here, and my fiber is something this, right? And I only take vectors which are tangent to fiber, so to say. So this.
То есть проекция на базу захватывает еще и часть касательного пространства. И вот это ядро мы обозначаем как VE.
Проекция на базу, она не то чтобы захватывает, я беру ее дифференциал, да, и это будет проекция на касательное пространство в X. Вот. Я говорю, что ну вот у меня есть здесь какие-то вектора, которые, значит, обнулятся. Вот. Они обнулятся именно те, которые касательны к слою. Вот. Ну, грубо говоря, я в каждой точке просто выбираю пространство касательное к слою. Вот и все. Okay, so now I can define connection. So a connection, and it's also called in the literature Ehresmann connection. Actually, this is like as from my knowledge, the most general notion of connection that you can imagine. Everything else is a particular case of Ehresmann connection. On a fiber bundle, well, E over X is a choice of a vector subbundle again, and we will call it HE. So this is inside, this is some bundle of TE. Right, this one is called horizontal bundle. Such that, well, HE plus VE is TE. So basically you have a canonically chosen vertical direction, and then the complement you can choose by yourself, and this will be a connection. Okay. So let us, we will see how it's related to the old connection when I have vector bundle, when my E is vector bundle. But well, maybe before that, let me introduce covariant derivative. In this case, what is this? So let me define isomorphism. So actually I have for each point in E, which is denoted as like this, and this is called horizontal lift. So this is map from where to where? From T pi of P x to T P E. Well, actually, since I'm saying isomorphism, it should be H P E. So notations, I don't usually write for a fiber, right? I usually write parentheses and P here. So my P will go here just to save some space with parentheses. Right, and so how I define it? By, so horizontal lift is, so I take pi, so I take d p pi restricted to the horizontal direction, and then it will become isomorphism, so I can take inverse. Right, so once I have chosen the horizontal direction here, I can take any vector here and lift it so it belongs to this H that I chose here. And that's what's going on. Okay. Now let me introduce. So now I need what is called pullback bundle, which is very easy notion that maybe we have to should have discussed before, but I never had too much motivation to do that. So if I have, so suppose maybe this is definition, right? Suppose that pi from E to Y is a fiber bundle, and I also have map F from X to Y. Then I actually have pullback bundle that is denoted F star E, and this is over X now. Then the pullback bundle is defined by the following is just again by fiber. So for each point in X, I give you a fiber. So fiber of F star of E at each point X is actually just fiber of E at F of X. Okay, so this is by definition what is fiber bundle. So I had the fiber, so the picture is like that. So I had E over Y, I had this map, so I pull this back to get a fiber over X, and this is very easy construction. So I just say that, okay, what is a fiber over this? I map it to here and look at the fiber of E over the image, and this is fiber over X. That's it. Okay, so once I get this, I can now at least understand what should be covariant derivative. So for S, so I take a section of E. Well, section of fiber is defined in the same way as section of fiber bundle is defined the same way as a section of vector bundle. No difference. Right. Then, and let me take V it's a vector field on X. So E is a fiber bundle over X. Let me take section of E and vector field. Let me define what does this mean. Covariant derivative with respect to V of S. So before, when we had vector bundles, it was again, it was again a section, right? So in this case, it will be something that will live inside gamma of S star of VE. So okay, VE is this vector bundle over E, where right, where at each point, right, I just take at each point of E, just take tangent space to fiber, right, and F star of VE, S star of VE, where should it live? Let me see. So S is a map from where to where? It's a map from X to E, right? So this is a section. Now I have tangent bundle, which is bundle over E, right? And then I have map S, which is, so I'm looking here, right, from X to E. Well, I actually should have like VE here. Then S star VE is actually bundle over X, vector bundle over X, right? Such that, okay, I have to look at this picture. For each point X, I just map lifted by section, right, up. So I fix my section, I take a point x, and what is the fiber for x? I lift it by section and consider tangent space tangent to fiber. And this will be fiber of S star V E. Okay. So this guy lives here. Define by the following. Okay, so I take this, and this is section in here, so I can consider its value at x, where x is a point in x. This will give me, this should give me some vector, right, at a tangent space of E at S of x. Okay, and so the definition is this. I take V, apply, push forward, and compute it at x. And subtract horizontal lift at Sx of V of x. What is S star? So if S again is a map from x to E, right, and then S star is a map from vec x, well, it should be a map to gamma of S star of TE. The following map, I just take, so S star of V at x, what's written here, is actually dxs of V of x. So what's going on? Okay, I take vector field V. Consider its value at x. All right? So this is my V. Its value at x. Then I consider its differential with respect to section. It gives me vector in here. Then I just take this and project to the vertical bundle. That's what I'm doing. So that's the definition of the covariant derivative in this case. So this is a projection along, so I take this vector, consider it differential, and then I decompose it into vertical component and horizontal, and subtract horizontal component. So that's what I'm doing. So I lift it by section and see what is the vertical component. So in other words, I define those sections constant which belong to horizontal component, right? Which don't change. Well, they're differentials, right? They don't change. They change only in horizontal direction. So that's it.
The result of the projection is a vector inside the fiber.
Yeah. So what's written here, right? This is a vector in a tangent space. So this guy is inside T, P, E. Well, actually, since I subtracted horizontal thing, right, should be VP. Okay. The question is now, how on earth is it related to the previous definition? Okay, let me not erase this picture. So how to? So I have to say, okay, let my fiber be vector space, right? So let E over X be vector bundle now. Then I claim that S star VE is isomorphic. So this is S star VE is again is a vector bundle over X. Is isomorphic to E. And I get here, when covariantly differentiate, I get, again, as before, section on E. So why this is true? Well, it's clear from this picture, right? I take S star VE and consider its fiber at X. What I said, okay, this is just tangent space to the fiber when I lift it by section, right? But when my fiber is vector space itself, right? Tangent space to a vector space coincides with this vector space, right? So before like what is generalization is that this fiber is not like, you should imagine it's not flat but rather something curved, right? And this tangent space is kind of vectors which do not belong to it, right? But when F is actually vector space, right, all these vectors are inside. So this is the same as just EX, because EX is just vector space. Right. Well, maybe I can actually write it like this. This is just equals to TF, right, at point S of X, right? And F, so it's just T of S of X of EX. But EX is vector space, it's just vector space. Right, so this is isomorphic to just EX. All right. But this is not it. If I take any, so if I consider this as fiber bundle and consider any connection, a Riemann connection on a vector bundle, it will not be the steel connection that we introduced. So we need additionally that our connection, require that our connection is called linear connection. So to get connection in the sense of old definition, informally speaking, we need HE to be what's called linear connection. Basically, we also, since we have covariant derivative, we can define parallel translation, and this parallel translation should be linear. So we require this. So if it's just any Riemann connection, it might not be linear. But if we say that it's linear, it means that we require parallel translation to be linear. Namely, so what does it mean? Let me go here. That is, HE should satisfy the following. So if I introduce the map m lambda, so this is a smooth map from E to E, defined by the following. If I take just P and multiply it by lambda, which is just a real number. Multiply in the sense that this guy belongs to a fiber, and inside fiber I can multiply it by scalar. So there's another element in the fiber, and in E, of course. So if m lambda is defined by this, then h lambda p of E is dm lambda of HPE. So our connection is kind of invariant with respect to this map, to additional structure on the fiber. We'll actually generalize this and see. Hopefully, we'll get. Well, I think to this we'll get a principal bundle. So you can consider not GLN, right? No linear transformations, but any Lie group actually. And there are so you can define in the same way connection that respect your additional structure on the fiber, selection of a Lie group. And this will be principal connection. But here so this is what it means in concrete formula, that my connection, RS1 connection respects linear structure on the fiber. So and we call such connection linear. And this actually gives us definition. You can check that, well, you can take this nabla and check how it acts on S multiplied by F, and this will give you a formula like with Leibniz rule that we got before. Okay. Okay, I promised you to define curvature, so let me define it, and then we don't have time after that. Okay, so let me define curvature. So first I will need two maps. First one I denote by K, and this is just a fiber-wise projection to vertical bundle. And H is fiber-wise projection to horizontal. So these are fiber-wise projections. And well, since I have this maps, I also have maps which are denoted by same letters. So these are from maps from vector bundles on vector fields on E, right, to vector fields on E. Basically, K, if I have a vector field on E, say Xi, right, it is some, I can look at it as a map. So vector field on E, it's a map from E to TE, right? And I can compose it with K. And this will be another map from E to TE, so another section, right? So that's just it. right? So Xi is a section of TE. So I look at it as a map from E, right, to TE. Right, so I take first this map and then compose it with K. Well, VE is inside TE as well. So I get this is also becomes a section of TE. And also for H I can do the same. And then I define the curvature. So maybe let me. So I would like to say curvature tensor. For that, I need this easy statement that the map omega h, I will denote it. So this is from the well, it takes a pair of vector fields on E and gives me another vector field on E. How? Defined by, so omega h, for some technical reasons I need minus here, I take k of the commutator of two vector fields, h of psi, h of eta. Well, this is omega h of psi eta, right? So psi and eta are two vector fields, and I get the third one, this one. So I take psi and eta. This will be h of psi and h of eta in this sense is a pair of, again, of vector fields on E. I can apply k. Well, I can compute commutator of vector fields, apply k up to minus sign. This is what's called curvature tensor. But to say that it is tensor, I need to see that this map is C infinity of E linear. Well, to see this, it's actually simple because, well, when you compute commutator of vector fields, right? Well, you commute, and well, there are coefficients of this vector field, coefficients of this vector fields. The only nonlinear dependence on coefficients may arise if I commute and this vector field, say, acts on coefficients of this vector field, and the other way. All right? But when it acts, it will be derivative, right, of coefficients, but multiplied by something in horizontal direction, which is then killed by k. So that's how it works. So the only dependence. So maybe I even have like a formula here.
What is H?
What is H? Yes, H is this map. So and I look at it as map from vector fields on E to vector fields on E. Yeah. So I take psi. So I can compute omega h, say, of f psi and then eta. So I multiply psi by f, which is a smooth function on E. Then what happens? I would like to see that what happens. Just I can, erase it here and write here. But this is. I have this form, this term, so it will be omega, so f of omega h psi eta plus So I multiply xi by f, right? So the only thing that will not is not in here is when. So in commutator I have also well, composition of this and this, right? So this can act on f, and this is what can screw me my linearity. So basically I will have k of h of eta applied to f, right? So this vector field can act on functions. It will give me another function. Well, function times h of xi. Right, so when I commute, I will get something like this, right? But you see, this function times something horizontal that is then killed by k. So this is then goes to 0. And so you really have a linearity of f. So this is proof. And now, so therefore omega h is section, right? So it's actually two form. So and definition, the two form omega h. Well, it is section of, it's two form on E, right? Section of this, and it takes values in TE, right? Because it gives me, well, another vector field here. So it's two form because lambda 2 T star is here. It's called the curvature form. No, just sometimes we just say curvature, and this is it. Right. So yeah, okay, I have to stop, but we'll see next time that if the curvature is 0, then a lot of good things happen. For example, like parallel translation around closed paths locally is 0, is identity. And your connection, if you have linear connection, then your linear connection is locally trivial as well, meaning that you can find some locally some basis of sections that your Christoffel symbols are 0. And yeah, in this generality, it's just consequence of Frobenius integrability theorem. So that's why I wanted to go fiber bundles. Okay, let's stop here. Давайте запустим листочек.
Я не знаю. Просто факт, доказательств.
две задачи очень важные, которые я решаю. И дальше их решение доказательства. Просто интегрировать а это процесс, который решает задачи. Это не связано с другими. Если было бы связано с этим, то жестко. Да. Но тут наверняка 2 миллиарда ошибок и еще не дописано. Скажем так.
Как я вчера у вас проблемы.
Да.
Это значит нужно минимизировать по УД. Это что держится?
Отображение.
С какая еще? Мира, где мир живет.
На X.
Кто X?
Любое пространство очень хорошее. Вот, и вот это важное условие, то, что мы выбираем R вот с вот этим ограничением. То есть эти выводят из одну меру в другую.
Это вот это половое какой мира?
Слушай, подвал.
Короче, уже как мира на парах.
А в том-то и дело, что смотри, в чем прикол. Это вот можно задачу сформулировать так. Вот у тебя есть одна штука, у тебя есть вторая штука.
Уже вот на график.
Вот это как бы да, отображение теста. Можно так сделать. А можно как бы сделать две случайные величины и моделировать их совместное распределение. Заданным названием. Но вот эта задача, она получается более общей, чем то. Потому что здесь может быть дискретное распределение, и дискретное распределение непрерывно, ну вот под таким отображением никогда не перетащишь его непрерывно. А здесь можно так сделать. И в этом прикол.
Ну тут еще условия на 3 есть.
Здесь
Тут вообще никаких условий.
Здесь просто должно быть совместное распределение данных. И вот прям по крайней мере, как раз мере на x, y мы не интегрируем.
Это было самое прикольное.
Вот, но это базовый типа такой, ну базовый. Я дошел до такого, короче, вот ты поэтому в один у меня не может быть.
Так, все расписались.
Еще нет. Про экстремально, да? Ну, мне очень интересно послушать.
Нет, так просто пишешь, не верю. Ну только надо учитывать.
Так. Ну, давайте.
Нормально.
Да, давайте. Еще надо первый записаться?
Допустим, что
Давайте вот это первое.
So we should have proved that for any cheat connection, some equation holds. It's nothing like something like that.
So G with upper indices is just inverse of G with
Yeah.
lower indices. Yeah, okay.
Inverse, you mean
Just matrix inverse.
ну,
В смысле, я понял. Инверс это обратно.
ну или то же самое, что сопряженный базис.
Сопряженный базис это...
По сути.
Ну, в смысле, двойка.
Ну, двойственность, точнее, да, двойственность.
Ну да.
Yes, it's inverse matrix. It's also true. Right, firstly, we can say that this equation holds. I think it was proved in lectures.
Sorry.
Or maybe not.
What are indices on the right? You just cannot.
E, G, S.
This
On the right. Ji. So you have symmetry in ij.
Yeah.
Yes, but this is because of what?
This is because of first condition on
Which is what condition?
the Levi-Chiric's connection to be good with.
Yeah, so this is just means that connection has no torsion, right? Yes.
Yeah, then we take second condition.
By the way, I wonder what would be a good picture, like how can one understand torsion? Like
What is torsion?
torsion. Yeah, torsion is this thing that like if you just erase equality, right, and put minus sign, this would be torsion.
No, even in Russian.
Значение.
Yeah, second condition.
So I would think maybe how you feel kind of. So if you go a little bit from the field, how stars rotating. So if somebody tries to take this poison, try to rotate it.
And this is second condition.
So this is basically
Yeah.
invariance of G with respect to connection. Yes.
And if we like take just something called this, then we will have some interesting formula. Alright, let's try to calculate left and right sides. By left will be
So on the left you will have d over dxi acting just i's derivative, right, of g jk.
something
Yes.
like that.
Yes.
And right side is something called this, but we will have to rewrite indexes to make two.
So if you apply nabla d over dxi to d over dxj, right, we will get gamma.
I think something like that.
Yeah, so maybe it would be completely clear after you write what is nabla of d over dxi applied to d over dxj. So nabla of, say, zx.
You mean this?
Yes. When you take z and x are like that.
Насколько я помню, license.
So k is fixed, to match the formula on the left, you should write s. I think.
Ah, yeah.
XS. And some over S, right?
Yes.
And so then, after you write this, it's clear that what you wrote there is.
Yeah.
Okay. Mhm.
But by writing this, I mean that there is a sum of
Over
same
repeating.
index.
Okay.
Yeah, and if we take three such formulas only with changed indexes, we can write three equations.
Yeah, so you have gamma of ij, gamma of ik, and gamma of
Yeah, something like that.
gamma of jk, right? So you have again,
Yeah,
as
we
in-
input this. We get these equations by not only permuting something and also changing L A to E, no, E, I to L.
Sorry, say it again, please.
We change I
Yes.
to L
I to L. Mhm. Mhm.
because then when we solve this,
Mhm.
we already can see that because of symmetry, these things and this
Mhm.
will sum up to 0.
Mhm.
So we will have only what? Only sum of these three
On the right hand side,
and the sum of this.
which are the same.
Yeah, which are the same.
Mhm.
And if we then write this sum for every L and sum up everything, then we get this thing equals.
No, you don't have. You just multiply by GSL inverse, right?
Yeah, and also we
Before you
multiply-
sum, before you sum, you will sum.
Yeah,
Be,
you're right.
yeah.
We have to multiply first by this thing
And
and
your I is
S.
Oh, yeah, okay. Mhm.
And then we get
So you have to change S to I,
something like
or I to S. So on the left you
yeah,
have
yeah.
I.
Then we get something like this
Yes.
and sum over L. And this thing will be not 0, only then e equals to n. So
I
we get
equals
to IGC. If we divide this by 2, we
So
get
I think in the upper, so G, not GSI, but GLI. And they will have,
GL.
No.
Yeah, GL. Yeah.
yes, and then you have delta SI, and so you S on right SI.
Yeah, only you can see that this we write GEN, but this we write GLE, but because matrix is symmetric, it's the same. Any questions?
Okay, number 2. Ливон. Миша, у вас чего не получилось в первом?
Да, что-то. У нас сейчас функция была какая-то ошибка. We're asked to show that the Euler-Lagrange equations give the geodesic equation if the curve is parameterized naturally. So consider the Euler-Lagrange equations. And we are asked to calculate the natural parameterization. And to see what happens if we plug the natural parameterization. So the proof relies on the fact that
So what is it? The square root of what?
the
On the
Lagrange,
right. The Lagrange?
yes,
Don't you want the Lagrange to be square root of actually G?
so you mean that this?
Yeah. So I mean, the way I define Lagrange is square root of the metric. Well, maybe you want something else, but
Give me a second. I want it to be
so Lagrange equations they work if you try to minimize functional, which is integral of Lagrangian. So Lagrangian is the square root of what you like. Right. Yes.
So my proof relies on the fact that if we have consider two actions. The first one is this, and another one is
this. Then minimizing them. Gives the same order Lagrange equations.
This is if your L does not depend on T.
Yes, and L does not depend on T since we have a natural parameterization.
Yeah, the bottom one is actually called energy or something, right?
Something like this.
Yeah.
Yes.
Okay. If you wish. But you actually can do it in straightforward way as well.
What again?
You can do with energy or you can stick with usual Lagrange and do it in straightforward way as well.
No, I want to do it with energy.
Yeah, I mean,
since
yeah, okay, that's good. That's good.
So let's just write down the equations. The first one is the derivative of the squared Lagrangian over the xk. It is what? It is, let's here write the squared Lagrangian. The sum over gij xi dot xj dot. And now we want to derive this with respect to xk.
And Gij depends on x.
X.
So Lagrangian you'll have to take partial derivative in x, right? So your dependence on x is actually in Gij. That's important.
Yes. Let's derive it. The derivative goes into the sum, and we obtain the sum over all ij of xi dot xj dot and the derivative of gij with respect to xk. Now let's calculate the derivative of the squared Lagrangian over the derivative of xk. This is the sum over all ij of so g does not depend on the x dot, so the derivative goes here,
Yes.
and we obtain 2 times the sum over all j xj dot times gkj. Is it clear?
Two because it's the sum of, so you, no, I don't think it's right. Right, 2 is because of Leibniz rule. So if you take derivative, I can be equal to k or j can be equal to k.
Here I actually use the fact that this is symmetric. It would be something like this.
Right, and your Gij is symmetric, right?
And j is symmetric, so we get. And now we want to derive this with respect to the parameterization. And what we get? We get the 2 times the sum over all j's of xj double dot times gkj plus now we use the chain rule, the sum of over i's of derivative of gkj with respect to xi times xi dot.
Еще должно быть на xj dot.
Да.
Стой. xj dot.
Точно, все. Да. Так, ну и что у нас получается? У нас получается 2. So what we obtain the sum of 2 times the sum of this of xj double dot times gkj plus the double sum over all ij of xj dot times xi dot times the derivative of gkj with respect to xi dot. No,
With respect to xi.
Yes. So now we want to make this to reorder indices such a way that after we equalize this and this, we obtain the Christoffel symbols. How we are going to do this? We are going to write this term as the sum of, as two sums. The first one is the sum over ij xj dot times xi dot times derivative of gkj with respect to xi plus the sum over all ij xj dot xi dot times the derivative of gki with respect to xj. And then we equalize these two terms. So they obtain 2 times the sum over j of xj dot times gkj equals to the sum over ij's xi dot xj dot minus the derivative of gkj divided by xi minus the derivative of gki divided by xj plus the derivative of gij divided by plus the derivative of gij with respect to xk. And these are the Christoffel symbols.
You need to multiply by g inverse first. Right?
No.
So you have xj double dot times gkj.
Yes.
So your geodesic equation is actually x double dot is something expressed with Christoffel symbols and x dot I, x dot j. So here, to get the geodesic, you first need to multiply by g with upper indices to express xj double dot. And then you will get Christoffel symbols.
What is g with upper indices?
It's g inverse.
I actually don't know what it is.
It's a
Правую левую часть записать как произведение двух матриц, и это будет единственная правда.
Yeah, so you have G, you have to multiply this, right, by, well, you have to rewrite it, right, X, sum of J, X, J, G, J, K, and double dot here. But then you have to multiply both sides by G, K, whatever, some S, right, and sum over K. And do it with both sides, here and there. So this, so sum over K goes here, and you'll get, so this will be delta IS, JS. So inverse, I mean that sum over K of this is delta JS. So I will have the X as double dot on the left hand side. And here I will have G KS and sum over K here. And these are cosine series. So if you compare with problem 1, that's what I said. Okay, yeah, thank you. Yeah, it's actually nicer with technology. Okay, number 3, number 3. Николай, мне кажется, давно.
Это про геодезические будем показывать, что геодезические на гидрополической поверхности это вертикальные прямые и окружности с центрами на действительно прямую. Ой, ну не на действительно прямую, а Y равно будет. Так, вот такие окружности и вот такие прямые. Так, ну что, наша метрика имеет вот такой вид. Ну, я буду таких терминов, потому что у нас все формулы, они как бы через x, поэтому. Вот, ну, соответственно, обратная матрица тут будет. Вот так. Это нам понадобится, чтобы первую формулу применять для вычисления символов и крестов. Так, ну а зачем они нам нужны? Потому что у нас уравнения геодезические с ними. Если мы возьмем, хотим геодезическую, она у нас V2, ну H, это у нас H. Так, соответственно, у нас везде два индекса будут в наших формулах. То есть вот у нас геодезические имеют вот такой вид. Так, отрадность и символ крестов. Ну вот у нас, соответственно, две как бы, два уравнения будут. Один, два. Так, ну это концепция, я взял все. Так, ну вот, нам надо вот это посчитать, как бы. То есть тогда мы уравнение определим. Но вот как раз используемся формулы, которые первая задача. Это я также выпишу. Там индекс, кстати, удобно.
Что там индексы?
Сходится, ну,
Да, сходится.
ну, да, что не надо там. Вот так. Так, ну что, ну подставим. То есть, ну я посчитаю какой-нибудь пример. Я, наверное, тут как бы есть симметрия, я просто не умею пользоваться. Вот если 1, 1, 2, давайте определим.
Ну, какое-то большое число нулей будет, наверное, да?
Да. Ну и я один пример, правда, досчитаю до конца, а остальные скажу. Так, ну вот, это просто постановка. Ну как мы здесь увидим нули? Вот это 0, потому что диагональный 0. Не, потому что у нас по x1 все у нас.
Да,
Да, по x1 у нас все.
Мгм.
Это 0, потому что диагональный. Диагональный. Вот у нас остается
В смысле, вне
вне диагонали, да, ну на обычной диагонали. А это у нас не равно нулю, только L равно единице. В общем, один член остается из всех. И он будет равен 2 минус 1. Вот. Вот такой у нас остается, и это будет у нас минус 1 делить x2. Вот так. Да.
Откуда минус?
Сейчас. Так, с минусом.
Минус 1 на x квадрат, это, наверное, все-таки
Так
неправильно.
а почему здесь минус? Здесь нет.
Да.
Теперь,
Да.
Вот. Теперь так. Отлично. Ну, я не знаю, если вы как бы я остальные могу просто выписать. Просто я не знаю, есть какие-то симметрии, которые помогают? Я как бы просто.
Ну, не считая того, что для 2, 1, ну, для КЖ равно. Ну, короче, них индекс можно применять.
Ну,
Ну, это там 2
значит,
два
потому что это, кручения нет. Поэтому гамма симметрично понижен индекс, например.
Включения нет, потому что из как бы.
Нет, это просто
Потому что потому что это величевито.
Ну да, потому что у нас метрика такая. И у нас связность такая, которая дает,
Да, потому что это величевито. Ну, все,
Хорошо, ну давайте.
Ну все, а дальше там надо как-то, наверное, больше даже смотреть. Да?
Несмотря на то, что сумма по n, символ будет равна, или сумма, или просто каждый символ будет равен своему с...
Каждый.
Так, и у нас нулевые есть. Так, ну вот, ну теперь все, можно теперь уравнение выписать. Так, они у нас какие получаются? Вот, для L равно единице, для I равно единице, вот сейчас пишу. У нас будет два одинаковых члена. И второе у нас будет два разных.
Так, ну вот что, ну вообще я как бы немного от ответа шел, когда решал эти уравнения. Так что...
Не, ну заранее как бы очень сложно, ну, мне кажется, додуматься.
Нет, да, то есть я говорю, то есть я выписал ответ и начал решать эти уравнения, то есть это так. То есть первый ответ это у нас будет... Да. Ладно, давайте выпишу где-нибудь тут. Вот. То есть первый ответ у нас... Первый ответ у нас будет... Первый ответ у нас будет такой. 1, 2. Это у нас...
Ответ в смысле решения?
Да, два решения. То есть первое решение это у нас... Что у нас константа? Теперь у нас x0, t. Ну, t это как бы переменная. А второе это как вертикальное, а вторые у нас линии как 1 плюс а плюс лямбда 2 второе равно там r2. Так, вот такое, ну, это как бы окружность, просто я говорю, что y, что центр ее лежит на y равно нулю. Ну, если общего вида взять, то есть я переписал это в общем виде. Вот так. Это, ну, как бы поменял, я поменял коэффициенты вот, в таком виде, чтобы так полегче будет. Так, вот, первое и второе. Ну хорошо, ну вот я сейчас буду обратную логику описывать. То есть я как бы шел от этого и пришел к этим двум уравнениям вот наоборот сейчас. Поэтому некоторые действия будут не совсем тривиальные. Но когда идешь отсюда сюда, то все понятно. Так, ну что, сначала у нас получается так, вот второе уравнение. Вот второе уравнение и первое уравнение. Первое уравнение.
Так, это мы умножим на гамма.
Да, это просто на гамма дочь. Так, отлично. Отлично. Ну что тут предлагается мне сделать? Так, нам надо получить, то есть нам два раза надо дифференцировать, чтобы две степени свободы то есть, получить. Так, какое предложение номер один? Чтобы получить b, вот эту константу. Чтобы получить b, это у нас давайте я буду от обратного, чтобы было понятно. Давайте продифференцируем. Так, вот, убрали одну степень свободы. А убрали. Теперь хотим b убрать. Ну, b убираем. Деля на гамма-1. Это просто перенесли. Вот, кстати, да, вот просто перенесли. И
Делить мы, кстати, всякое можем, потому что мы живем в верхнем полу.
Да. Я так немножко. Это важно. Теперь поделим, да, я тут немного поделим на гамма-1. Вот здесь мы предполагаем, что гамма-1, что мы переходим во второй случай, у нас гамма-1 не равно нулю. Потому что если гамма-1 равно нулю, это вот это получится. Ну, я потом поясню. Так, что делим на гамма-1 штрих. Ну и дифференцируем. Тогда у нас гамма-1 штрих плюс 2 гамма-2 гамма-1 штрих равно нулю. Мы посчитаем. 2 штриха на гамма 1 штрих минус гамма 2 на гамма штрих гамма 1, 2 штриха. И поделить гамма 1, 2 штрих во второй. Все, это просто считать. Теперь умножим это на гамма 1 штрих. Гамма 1 штрих во второй плюс гамма 2 штрих во второй плюс гамма 2 штрих минус дробь оставшийся. Вот, но вот эта часть, она напоминает второе вот это уравнение. Так, поэтому мы возьмем вот это и заменим вот по этому уравнению на гамма штрих 2 во второй. Получается 2, гамма штрих 2 во второй, минус вот это оставшаяся дробь. Так, первым уравнением воспользовались, теперь вторым надо воспользоваться. Вот этим. Ну, давайте вынесем гамма 2 штрих. В общем, вот этим надо воспользоваться. Сейчас. Надо вынести и получится гамма 2 штрих минус гамма 1 штрих гамма 2 равно нулю. Но это вот как раз и есть второе уравнение. Вот это. Так, ну какой итог этим вычислением можно подвести? Что
эти уравнения, из них следует.
Что если мы знаем эти уравнения, то это является решением.
Ну да.
Да. То это является решением. Вот. И также является решением так, и еще является решением то, что гамма 1 штрих равно нулю. Ну, соответственно, гамма 1 штрих это x0 некоторые фиксированы. Так, теперь, да, из этого надо еще вывести это гамма 2, это t. Нет, ну какая, нет, ну у нас гамма и какой-то гамма 2, это я тут t написал, но на самом деле это же от параметризации зависит. Просто гамма 2. Параметризацию можно к линейным системам так делать, не обязательно. Ну вот, соответственно, вот получили, что у нас есть либо прямая, либо прямые, либо округлые.
А других, кстати, почему нет?
Сейчас. Если у нас
ну, локально, да, из единственности. То есть мы, в принципе, там фиксировали где-то.
На самом деле, вот мы тут подошли, мы все однозначно. То есть, может, если записывать в обратную сторону,
да,
я думаю, что это однозначно. Что любое физическое будет при этом.
да, если вот начать с этого, потом
можно все эти
раскручивать.
обратно.
Да, ну я не знаю, как бы это понятно.
Ну, а можно действительно воспользоваться тем, что мы знаем, что как бы, локально, по крайней мере, у нас есть эти нормальные окрестности, у них вот геодезическая только одна. Вот если взяли две точки, то как бы, если они на вертикальной линии, ну, в принципе, если две точки, вот такой кривой одной только можно связать, и все, других нет.
Да, ну да. Либо аркой, либо прямой.
Ну, если они на вертикальной, одна под другой лежат, то тогда прямой. А если вот так, то тогда...
Ну да. Ну да, ну они на самом деле в этой модели они как-то различаются, но вообще не обязательно. То есть какой-то там вроде в круговой правильно, что в круговой модели они одно и то же.
Да. Да, мне нужно какое-то преобразование сделать, свернуть это в круг.
Да, и тогда это...
Да, если будет окружности, да, которые под прямым углом к кругу подходят.
Тогда это одно и то же.
Да.
Так, ну вот.
Просто switch to Maybe may I ask you to do the fourth one? Only also. It was a while since you presented.
I have to show that for given metric and just metric for general linear group, the corresponding identified connection would be also defined before, and then I have to show that exponential mapping corresponds to just matrix exponential. So we have such metric. Then we are going to apply a formula from previous lecture that states that we can define our connection for arbitrary three vector fields via metric and v-vectors. It states that in general, for fixed point on three vector fields, we have something like that.
In some literature, I saw that this formula is called Cajun formula. But maybe it's not applicable for Libras.
from here we have that is our metric does not depend on the choice of a point on the group. These three terms have to be zero since vector field elected as a constant on them. So we have non-zero terms only here. And by definition, they have to be some traces.
Traces of commutators of corresponding factors.
Yeah, right. Here we have
And the zero means you have to permit.
yeah, I have to permute with some signs. Corresponding just to this terms.
Yeah, with signs.
Yeah,
So the signs might be different. Okay.
so we have minus this plus this.
And the fact that the commutator of the vector fields VA and VC is V of commutator of matrices is just, you need to check it.
In some
Just complete differential, right? And,
yeah, right.
and linear terms will be just commutator of corresponding matrices, right? Okay.
Yeah, then we would like to use this fact about trace to get rid of some sums. And then we obtain simply and if we get back to go back to this definition in task, it says that connection has to be hence left hand side of this formula says that it should be equal just trace that is exactly
Yes. Okay.
right, and then
So we're done, right? This is, we checked that this is exactly reaching the connection.
yeah, right. And then we have to show that the exponential mappings are just the matrix one. To do it, we may just note that our basic vector fields are defined as left invariant ones, meaning that can be rewritten in coordinates as something like that. Hence,
well, I'm not sure what does it mean. So VA applied to B should be something from the tangent space to B.
yeah, right.
So you have to somehow identify tangent space to B with matrices. So
Ну, типа, ну, просто...
So it's a differential. So it is written, right? The differential of a curve of B
Yeah,
times 1 plus
Just
TH.
Yes, okay.
So we just may consider the provided curve for repeated array. And note that it has to be the following form. Hence, should be equal to just corresponding vector field in point of exponent. Yeah, right. This is exactly this. And then this vector field is extension of this curve. But then connection has to be evidently zero since we have in bracket of two identical terms. Hence, this is exactly the Jeffreys.
Okay. So, any questions? Actually, this is all very helpful when you study Lie groups, and you study some you study some integral formulas on Lie groups. All this theory of Lie groups as Riemannian manifolds. Have a lot of applications there. So. Anyways, have some time and one problem left, which is number 5. There's one person who did this, Nikolai Karenin. No, two persons who also did it.
We need to show that we have a hole inside some normal neighborhood of 0 inside the tangent space at the point P to the manifold, to a Riemannian manifold M with the metric G on it, and show that any geodesic gamma, so you can call U maybe N, and U will be the X at P. Okay, and gamma is such a curve from the closed interval to U. Yeah.
Okay.
And it is geodesic such
That maybe even not to you, but the whole M doesn't very matter. I think.
so it's enough to show that gamma dot at point at some point, well, we can write it just like this with any vector this point that is tangent to the geodesic sphere. Well, tangent to x of SR. And well, if to write it rigorously, it will be this, but I'm going to write it like this and omit the point. Okay, so in the lack of time, I can.
We need to show that this is 0, right?
Yeah, of course. This equation holds true. Okay, in the lack of time, I want to describe my idea. So the standard idea, I guess. Yes. Okay, we have some pictures. So we have P and SR will be something like this. It hasn't to be a round sphere, of course.
Well, it is round sphere if you, but in the sense of Riemannian.
But
There's only one notion of being a sphere, right, on an arbitrary manifold. Riemannian, so.
well, and we shall go through something that is a generalization of the fact that, well, from the Euclidean term. Well, okay, we have a geodesic gamma, and we need to show that, okay, this is some gamma naught, and we prove that, well, you have to believe me that this is the right angle, yeah. Okay, and what we are going to do, we will, well, how to define a vector at a point on a manifold is to choose a curve, sigma from this open interval into x of SR. Okay, some curve will be here. And we want to consider a map, usually denoted as gamma. Okay, we will not use Christoffel symbols here, so from the product of this open interval and this closed interval to U, and basic idea is to see that we can not only see this one geodesic, but the whole collection, the whole family, such. And of course we will have these curves, also something like this. So, and for fixed S and T, gamma S of T is just, for fixed S, this is going to be
So S is parameter on unit sphere, so to say, right? And 0T is 0 parameter, which is radius.
Yeah, for fixed S, this is our geodesic from point P, and for fixed T, it's, well, our initial curve in the sphere, just transmitted.
So this is what was called the spherical coordinates.
Yeah.
In last time.
Just a grid. Well, okay. As like polar coordinates. Yes. Something like that. Okay, and the idea is, well, see that this vector x is just d by ds of gamma s of t at s naught for our fixed initial geodesic gamma from here. Well, t is t naught. This is our x, and gamma dot t naught is just d over dt at the same point of gamma s of t. Okay, and now the idea itself is that d over ds of gamma at point s equals naught and t equals naught, the dot product of this with at this point is 0, and this whole expression, just write it like this, is independent of t. So when we travel along the geodesic, the zeroness of this dot product is conserved, and so we get 0 of the dot product here, hence the
right is independent of t.
Мы хотим не независимость от S, чтобы... Ну, мы хотим, может, наверное, независимость.
фиксировать S?
No, as it's written, doesn't depend on S and T anyways. So it's just some... okay, you fix S equals 0, and you say it's independent of T.
I haven't constructed yet gamma s of t, which will be
Yes, okay.
t of t naught, sigma of s, and it is a consequence of choosing the right coordinates on U, well, to be normal coordinates where the geodesic equation, the coordinate representation of the geodesic is just some for V1 Vn, some vector V, some fixed vector V that defines our geodesic.
It's so clear that still that this is independent. So if I take derivative with respect to
Time?
T,
Yeah.
then it's linear in T, so that's why, right? So your gamma is kind of linear in T. So it's, of course, then derivative doesn't depend on T.
Yep.
Okay.
Yeah.
Сейчас, можно еще раз? То есть мы получили, что когда мы S и T кладем равно нулю, то тогда действительно будет 0.
Да.
Но мы хотим это перенести на S.
Вот сюда. Вот сюда. То есть отсюда вот сюда. На сферку.
Это получается параметр T равен T большое. Да?
Нет, T0. T большой где-то там. В смысле, на самом деле U-то у нас побольше. Побольше, просто мы именно сферу внутри же имеем. Вот. Ну, как бы Т0. Можно было здесь, наверное, до Т0 идти, но просто Т0 она там разная для всех, поэтому.
Как я, значит, на лекции, on the lecture we had this, that phi star of G is dt square plus omega sum of I, omega I bar squared. And basically, when you take a vector, so when you compute this, right, you take and plug into here two vectors, right? One is so this all means on this kind of 0 delta times s, right? Where s is you actually in the lecture it was of radius 1, right? But we can change radius here and maybe rescale delta. It will be not the same thing. So what we are doing is that we need to take tangent vector to SR and tangent vector to this. So in these coordinates, what we plug into here, two vectors, V1 and V2. Right, V1 in these coordinates will be something like d over dt 0. Well, maybe with some coefficient here, cd. And V2 will have 0 component corresponding to this coordinate. So this is vector is going along geodesics. And this and V2 is tangent to S. So it will have something here in the second component. And so when we plug this into here, right, this 0 kills you this guy, and this 0 kills this guy. And overall it's 0. So you don't have cross terms here, that's the whole point. So because when you plug in, this will in cross terms what could be not 0, when this plays with this. But there is no cross terms. So no performance is 0.
Ну, это объяснение, почему вот этого достаточно показать.
Ну, это объяснение, ну как, это объяснение, как, значит, вот это следует из формулы, которая была на лекции. Но здесь чуть по-другому сделано все-таки. Я даже не знаю, ну, наверное, вот этой штукой не воспользовались. Вы говорили, что вы придумали гамму, да, такая она константа. Вот. И посчитали здесь, а значит здесь она такая же.
Ну да.
Окей.